Hi, welcome to the chat. Another chat video. This one is regarding the development of the software for the Black Horse or Dark Skies at Night. My camera zoomed in on the application on the screen. I don't have a way to put this directly to video, and the camera has a very narrow focusing range at this distance. And so what I'm going to do is show you a different half of the application at a time. What's going on? This application needs improvement right now, but right now it's good enough to show you what I've been doing. This little disk over here represents a spiral galaxy, or a galaxy, and this is the distribution of stars. And you can see there's more stars at the center, and it doesn't look like a spiral. I'm just going off a regular distribution. And over here is the location of the Earth. I don't know if you can see the little red dot in the camera. And I can pick a uniform density of stars where the density of stars is the same throughout. This little number here displays the ratio of the nighttime sky brightness with this distribution. In other words, this is how much more brighter the night sky should be as opposed to what we actually measure based on the distribution of stars. Okay, this is the number of stars, 400 billion. This is how much I'm dividing up the universe. You'll see what that means in a moment. Okay, we have a uniform distribution just as a check. The uniform distribution turns out to be the darkest night sky because why? You're spreading the stars evenly over the 100,000 light year disk of the Milky Way galaxy, and so the stars are on average farther away from Earth. Then you have a normal distribution, which is just a statistical distribution, and this gives 10.4 times as bright as a night sky should be over what we're measuring. And again, this is for 400 million stars. Even if I put 200 million stars in here, because they say the Milky Way galaxy is anywhere between 100 to 400 million stars. Okay, it's still, even if you cut the number of stars in half, the nighttime sky should be 5.2 times as bright. Okay, and what I can do is I can include sky glow, which we'll describe in a moment, and that reduces it a little bit more. Then I can clip the backside of the universe. In other words, you could say, well, since the Earth is here, we can't really see the backside of the universe because that's going to be obscured by the side of the universe we're on. Okay, we get rid of that. It doesn't change that the nighttime sky should be at least 4 times brighter with all that stuff. Okay, and then here's a luminous distribution. Let me just go back to these other guys here. The luminous distribution is the measured luminous distribution over galaxy. If you go to Wikipedia, they'll give you the equation for what the luminous distribution. This should be the proper distribution, and we'll talk about that more in a little minute when I show you the bottom side of the screen down here, which gives other information. Let me just introduce all the top side stuff. And then you have the Navarro-Frank-White distribution. This is a Navarro-Frank-White distribution. This is the distribution that is necessary to have the matter distribution in the universe, in the galaxy, such that the stars have the same speed as they roll out. There are stars out here, you just can't see them because compared to the scaling of the color model here, these are so far down, it's near black, it's almost, but there is stuff out there. But if we compare the Navarro-Frank-White to what they measure as the luminous, okay, the luminous is still more toward what we would expect as the nighttime luminous. We go to this one, which is in order to fix the problem of the dark matter, and that gives us an even worse problem because instead of this, where all the stars are like, you got lots of stars very, very, very far away, by concentrating most of the stars on a little pinpoint at the center, you're actually bringing a lot of stars that would have been farther away even closer, and so they're going to increase the nighttime brightness of the Earth. Okay, but let's just keep going to, this is the luminous. This is the measured based on optical luminance of the distribution of stars. So we're going to stay with that for the rest of this discussion. Now, there's another button here called contribution. What contribution does, it says, well, where is the contribution, based on the fact that you have the inverse square and the inverse square and the distribution of stars together, where is the majority of the distribution? You can see it's mostly close in. But now if we go back to the Navarro-Frank-White, and we look at that distribution, we see because of the concentration of stars at the center of the galaxy, that has a big impact on our nighttime sky. So we can be sure that Navarro-Frank white distribution is not right for visible matter. Granted, this Navarro-Frank white is made mostly for where the dark matter is, so it's really not applicable. I just put it in there as to see what would happen. The luminous is the measured distribution of stars by luminosity. Now, the number of radial segments, you see how it's like a little chunked out here? Oh, and don't mind this. This looks like there's some kind of 3D going on. This is just the way the color model chose. This is a false color representation because this is a logarithm, and so each one of these logarithm, this is, I believe that's -10, -20 dB, and these are all in decibels. Okay, so don't mind, there's not really a delineation here. That's just the way the color model played out the colors. This is continually decreasing in amplitude. There's no roughness here. That's just the way the color model chose the colors. It makes it look like there's a depression here, but that's not. That's just a color model I chose. Now what we can do is, if we increase by 10 the number of radial segments, number of angular segments, you can see these are the angles that were picked, and let me reprocess this. Okay, see everything's smoothed out up here? And actually it darkened a little bit. That means the inside came brighter. So in other words, more of these radial segments divides up the universe into smaller, tinier segments, and you get a much more smoother representation of everything. But you'll also notice that the nighttime sky got brighter. Let me go back a second in case you missed that. This is where there's a problem in the software, and I have to go fix it. Okay, see, the more you divide up, the more farther away your neighbor stars. Your neighbor stars turns out to be the biggest problem here. And let me show you the bottom side of the screen so you can see what I'm talking about, because the bottom side of the screen has information that makes this. Okay, here, this is the measured nighttime lux. This is the computed nighttime lux based on the stellar distribution. This is the ratio, which you see here. This is the total number of stars that are accounted for. In other words, when we integrate over this area, we add up the number of stars as a check to make sure that we did no problem with the integration, that we ended up with the same number of stars that we anticipated for up in this box. This is the distance to the center of the closest segment. Okay, hold on, I gotta move the camera up. Okay, this is how we're dividing up all the little segments. Remember, you see these are all little segments, I can put less in here. Maybe do, I don't know, 30 angular and 20 radial segments. Okay, and you can see how these are all the little segments of how the integration process is dividing up the universe. And what this little measurement down here says, go back here, is that the distance to the center of the closest segment is 1,000 light years. Okay, and okay, this is a little bug here because I'm not integrating with enough. So let me put the number back up to normal. The number of radial segments, let's put 150. And the number of angular, 150. I'm sorry, I got it backwards. Okay. Okay. So this is saying here that the distance to the center of the closest segment neighbor is 571 light years, which is a lot. And the number of stars in that tiny little segment are 43,000 or 44,000. And that little neighborhood volume there is 6 million square light years. Okay, and if you take the average distance between the stars, it's about right. It's about 5 light years between stars. So see, now the problem is we're taking all of those stars, all of these, 43,000 stars, and because this is numerical integration, we're treating that as a clump of 43,000 stars that are 571 light years away. And that's why as you increase the number of, I'm going to increase the number of segments again, because that's going to bring all the segments closer. Let me do that and reprocess. See, now the nighttime sky went brighter again, but see now that now our closest neighboring segment is the center of it, 60 light years away. The number of stars in that segment is 436, and we get to about 5.2. So what's happening is the numerical integration is showing that your closest stars are your major contributor for this distribution. That doesn't help us because we need the contribution from faraway stars to be able to compute the viscosity. Close-in stars, but so what I'm going to do is improve this because, how do I say this? Something is wrong. Okay, let me just say it to you that way. Something is wrong. The stars in our neighborhood, the average distance between stars in our neighborhood is about 15 light years. If you take that there's about 53 stars, I think it is, within 50 light years, and you do the calculation, you end up with an average distance between stars of 15 light years. And the only way I can get 15 light years between stars is to reduce the number of stars to 10 billion stars. Okay, and then, but now we're like, the night sky is way too dark. We're 1/5 the brightness that we should be, that we measure. So, my friends, something doesn't add up. I think it might be my numerical integration algorithm. I'm going to do a fractal algorithm to take care of close-in stars, treat the close-in area better. And, I'm going to do that. I'm going to spend a little bit more time on that to improve this because it might be my algorithm. It's definitely have something to do with the near-in stars are important. But here's the end result of this. The end result of this is because the near-in stars are the major contributor to nighttime brightness, they're too close for us to use that as an estimate of loss, is what we were trying to get at. But this needs to be figured out just so we can have an understanding that the numbers that were given to us by scientists are valid. Because either there's too few stars in the Milky Way galaxy, or our understanding of where a location is relative to the center of the Milky Way galaxy is completely wrong. And so a little bit better simulation on this will, tell us a little bit in finer detail what's really going on, or if it's a mistake with the numerical integration. So I'm going to spend one more iteration on the software on this. It's not helping Ethereal Mechanics, but I want to make sure that that it's not my software algorithm that's causing this problem. Whereas in order to get the right, and I'll repeat the problem in case you kind of missed it. In order to get the average distance between stars to match what we see, which is about 15 light years between planets, I've had to reduce the number of stars to 10 billion. But then that ends up with too dark a sky. In other words, the measured sky, if the computation matched the measured sky, this would come out to 1. This is the ratio between how we compute how dark or bright the sky should be over what we measure. Okay, in order to get the right distribution of stars that match, I had to reduce to 10 billion the number of stars. Now we get 1/5 the amount of brightness at night. If I put in the number of stars that they say, let's say 200 billion, and I reprocess, the nighttime sky should be about 4 times as bright as what we measure. And the average distance between stars is too close together. So either one's right or the other's right or the algorithm's wrong. Something's wrong here, and I need to validate that it's not the algorithm that's causing the problem. Because if anything, from what I'm seeing here, by me improving the algorithm to take better acknowledgement of close-in stars, the nighttime energy should go brighter and brighter. Okay, so by improving the algorithm, I'm only going to show, I'm expecting that as I improve the algorithm, that I'm going to show that the numbers we're given for our place in the galaxy, or the estimate of the number of stars, is way off. Anyway, that's where I am right now. We're not going to make a teaser video of this because this can't be used for our viscosity argument anymore, unless, of course, improving the algorithm shows us that we were on the right track. It was just the algorithm hiding the problem. So I need to validate that and get that out of the way so I can get a true realization of if this is a way to go or not. So anyway, that's where we are. Thank you very much for your patronage.